Hello and welcome again. Explain why low temperatures favor the forward reaction in the Haber process. 4 years ago, I made this video. Yet still, the popularity of Le Chatelier's principle as an explanation for how temperature affects the rate of an exothermic or an endothermic reversible reaction persists in textbooks, on YouTube, and from all kinds of teachers. Students swallow Le Chatelier's principle. Sometimes they don't quite get what the teacher is trying to say. Some instructors are more skilled in presenting the principle, and as such, students feel very comfortable with it. But it begs the question, is this really an explanation of what is happening at the molecular level? Isn't it that Le Chatelier's principle is merely a tool, a predictive tool, an algorithm, if you will, something that just empowers the student to make a correct prediction? Yet, it provides no explanation as to what is happening at the molecular level. Let's take a look at how the principle is used once more. Here we have the classic exothermic reaction, the Haber process for the manufacture of ammonia. In the forward direction, it's exothermic, nitrogen and hydrogen to produce ammonia. Exothermic reaction, of course, means that heat is generated. We treat heat as a product. Now let's imagine increasing the temperature or adding heat to the system. We could treat heat as a reactant here, and if you add more heat, the system would oppose what you have done to it, so it would consume heat and go towards the left side. If you give a lower temperature, therefore, and less heat, in other words, the system would try to generate heat. And with that kind of explanation, students would very easily be able to predict how heat or increased temperatures are going to affect both exothermic and endothermic processes. But of course, it leaves us asking, where is the deeper understanding in all of this? And the ironic thing about it is, in the very same textbooks where students are being instructed to learn about Le Chatelier's principle, hidden in plain sight are tools like the Boltzmann distribution curve, the reaction profile diagram for an exothermic reaction. Bonds broken minus bonds formed equals the enthalpy change in a reaction. Pictures of molecules on one side of the reaction barrier and on the other side of the reaction barrier. But none of these are actually connected to this explanation as to why an increased temperature pushes the equilibrium from one side to the next, or favors the reverse reaction here in this Haber process. And putting Le Chatelier's principle aside, let's see if we could make multiple connections, starting from this reaction profile diagram here, which shows an exothermic process, reactants having more energy than products, and taking these calculations here and thinking that bonds have to be broken first of all. Energy has to be put in to energize this side, to cross this barrier, and then bonds are made. Bond breaking requires energy on this side, and then on this side, when bonds are made, a tremendous amount of energy, extra energy is released, and therefore you get this release of heat here in this exothermic reaction. Molecules are constantly moving across this barrier as they have kinetic energy of motion as a result of a particular temperature that they're at. They've got molecular motion. And if they have sufficient energy to break bonds and to cross this barrier, as it were, then they will do it. But look at this side. The barrier is much shorter than over on this side here. So at low temperatures, if you think of it logically, which side would have the advantage in this battle to get molecules over the barrier? It's going to be the side that has the smaller barrier to cross. So the forward reaction in this exothermic diagram here is much more likely to occur if the temperature is low. But let's think about increasing the temperature now. Increasing the temperature would not slow down either side. Both sides would get increased. But what we would have happening is there's a greater probability of ammonia molecules breaking their bonds and going back over to form bonds of nitrogen and hydrogen. And let's not forget, we have got the all-important Boltzmann distribution curve, which we can connect to all of this. Let's consider the low temperature as T1. Of course, noting here in this Boltzmann curve that T2 is greater than T1. So T2 is the higher of the two temperatures that we are about to consider. So T1 is our low temperature. And this short barrier right here is what's required for reactants to become products. And a much higher amount of kinetic energy is needed for products to become reactants. So that's why I have these two lines here. This black line here representing products going to reactants, and this red line here representing reactants going to products. This is a lower kinetic energy. You see here on this x-axis, it's a low kinetic energy for this red line. It's a much higher amount of kinetic energy needed for the ammonia to jump over the barrier here. So at this low temperature, T1, all of these particles on this right side of this red line, including this brown bit down here, they have the energy to go over the barrier. But going the other way, only everything here on this brown section here, only that brown section would have the energy. So a lot more molecules can cross the barrier from the left side to the right side or in the forward direction when the temperature is fairly low. Let's consider now using the Boltzmann curve and relating it to this diagram. We increase the temperature so that T2 is higher than T1. Suddenly we see a lot more of these particles on the reactant side have the probability of getting over. Everything on this red line right of this red squiggly one would have the energy to cross the barrier. So previously you had everything in the blue section. Now you've got possibly a doubling. Just looking at the area by inspection, it looks like the area is doubled. But look at the brown area, the area that had the bigger energy barrier to cross. From T1, where it was just this brown area, now with T2, suddenly it's gone up by about 3 or 4-fold. And of course you can use calculus to calculate these areas if you want to, but just by inspection you could see that the increase in temperature, what it's done is it's increased the probability of particles going over from either side by doubling on this side here and quadrupling possibly on this side here. So which side gets the greater advantage? Relatively speaking, which side is favored as a result of a higher temperature? And we come back to where Le Chatelier's principle could give us the prediction. But now we have a better conceptual understanding, connecting the Boltzmann distribution curve, the reaction profile diagram for an exothermic reaction, thinking about bond breaking, which requires energy, and bond making, which releases energy. And if we add an animation like the ones on PhET simulations to this, then we would actually be able to visualize molecular motion and do investigations into these temperature changes.